All right, so we're going to change gears a little bit and look at thermochemistry, the heats of reaction. Um, Energy you have to put in or energy that's released. Okay, so thermochemistry is kind of the little bit of the more specific term. Thermodynamics is the overall term of the science of the relationship between heat and other forms of energy. So thermochemistry is, like I said, a little bit more of the drill down a little bit more. It's the study of the quantity of heat absorbed or evolved by chemical reactions. So this could include things like reactions involved in food metabolism. So when all the energy that's given off in reactions when we eat food, burning of fossil fuels, just general reactions overall, energy that has to be put in to produce other compounds. So we're going to be looking at the relationships between chemical reaction and energy. Okay, so first let's define what is energy. You probably have a vague idea of what energy is, but energy is just defined as the capacity to supply heat or do work. Probably you've heard of different kinds of energy, so just take a minute and think about what kinds of energies you've heard of. Things like radiant energy, which is energy from the sun especially, or from lights, electromagnetic radiation, visible light, infrared light. Thermal energy is associated with the movement of molecules. We sort of talked when we talked about gases, we talked about molecules moving faster or slower depending on their thermal energy, what the temperature was. Chemical energy then is energy that's stored in the structure of a molecule or atom. Usually that has to do with bonds, forming bonds, breaking bonds, things like that. Okay, the law of conservation of energy states that energy cannot be created or destroyed. It can, however, be converted into a different type of energy. Okay, so the two broad types of energy that you've probably already heard about are kinetic energy, which is just the energy of movement, or potential energy. Potential energy is the energy an object has because of its relative position in a force. So usually that force, not usually, but one example of that force is of a force field of force is gravity. So if I lift something above my head, it increases in potential energy because it's higher up. So clearly, if I drop a book from a foot off the floor, it's quiet, but if I drop it from 6 feet from the floor, it's got much more energy. But there's other types of potential energy depending on its condition or its composition. Sometimes we call the energy in a bond as a type of potential energy, something that can be used later. Okay, so let's just talk real briefly about kinetic energy. So we know, again, kinetic energy has to do with the energy of motion, and kinetic energy, here's the formula we can use. Kinetic energy is equal to 1/2 mv squared, where m is the mass of the compound, or the whatever we're talking about, and v in this case is velocity, or in other words, it's speed, how fast it's going. So mass and velocity. So kinetic energy is dependent on both of those. So we know, for example, if we have velocity, if we have one car that's going at 60 miles per hour and the same car going 15 miles per hour, we know that the one going faster has more kinetic energy. We also know that it's directly related to mass as well. So for example, if you had a small car or a semi-trailer moving at the same speed, the semi-trailer obviously has a whole lot more energy. And if you think about them crashing into a wall, you can imagine that the semi-trailer, because it's heavier, has more kinetic energy. Just kind of informational, the unit that we use for energy is joules. A joule is defined as a kilogram meter squared per second squared. So you can see here the unit for mass, kilograms. The unit for mass is kilograms. The unit for velocity, one unit, is how far for how long. So meter squared per second squared is a real common velocity. So if you have your mass times velocity, you get kilograms times meter squared per second squared, which is equivalent to a joule. And so that's the unit that we usually use. Oftentimes we'll use kilojoules, where 1,000 joules equals 1 kilojoule. So that would be the most common. Probably another unit that you've heard of is the calorie. Traditional energy changes. The calorie is a non-SI unit, so we don't. You may see it in the book. You may see it discussed about. Mostly we'll be using joules, but just for your information, 1 calorie equals 4.184 joules. And just a further note, when we talk about calories, you think about the calories that you eat. A calorie that you eat is actually a kilocalorie. So it's usually given the capital C when we're talking in science. Yep, so nutritional calorie, capital C, is really 1 kilocalorie or 1,000 calories. Okay, so let's just do a real quick problem. So suppose a person weighs 130 pounds and is traveling in a car at 60 miles per hour. I've gone ahead and converted. I kind of use English units so that we can have it in mind what we're talking about, but then convert it to metric unit. So 130 pounds is the same as 59 kilograms. If you're moving in a car at 60 miles per hour, it's the same as 26.8 meters per second. So the energy is 1/2 m in kilograms times velocity squared, so 26.8 meters per second squared. Notice that when you multiply that out, you get the units kilograms meters squared per second squared, which is the same as a joule. So 2.12 times 10 to the 4th joules, or 21.2 kilojoules. This is a simple calculation, most likely not something you'll have to do, but just kind of keep that in mind. So then potential energy, remember, energy depends on its position, like its height, in a field of force, for example, gravity. So it's not the only kind of potential energy, but that's probably the most common that we talk about. So for example, if a water of a given mass is at the top of a dam, and that means it's high with respect to the earth, it's high up, so it's got a position h, height, and it's in the gravitational field, and the gravitational field we'll call G, and there's a constant for G. G is a constant on Earth anyway. There's different gravitational fields on different planets, but here on Earth. And so to find the potential energy, it's equal to this equation, mgh, where m is mass again, G is that gravitational field, which I said is a constant, and then h is the height. And again, what you want is units that are standard. So we want height in meters, we want mass in kilograms. So the gravitational constant is 9.8 meters per second squared. So you can see here that if you do mass in kilograms, and gravitational is in meters per second squared, and then you multiply it again by meters, you're going to get kilograms per meter squared per second squared, or joules. So again, you'll have your unit in joules. So let's do a real quick example. Consider a woman on a bike weighing a total of 250 pounds, or in other words, 113.4 kilograms. And she is standing at the top of a hill that is 150 feet high, or 45.72 meters. how much energy does she have by virtue of her elevation? Potential energy is equal to mass times the gravitational constant times the height. So if we multiply that out, like I said, we get kilograms times meters squared per second squared, which are the same as joules, or we can convert that to kilojoules if we have a big number. Unless it's specified, it doesn't matter to me if you use joules or kilojoules, as long as you put the proper unit. Sometimes the question will specify it, say tell me in kilojoules, and then you do have to be careful. And just some other little side bits. So if your mass is not in kilograms to start with, you'll have to convert it to kilograms. If the height is in something else, you have to convert it to meters. Okay. So anyway, and then if she starts coming down the hill, what happens? Her potential energy decreases, but it doesn't mean it doesn't go anywhere. It's converted. So it's converted to kinetic energy because she's moving now. It might also convert to heat energy or frictional energy with her tire on the road. So it's definitely much more complicated than what we'll ever get into, but just kind of have an idea of what we're talking about. Right, so let's talk about heat for a minute. Of course, heat is a type of energy, but just keep in mind heat is different from temperature. So don't keep those two things in mind. Keep that in mind. Heat is defined as the energy that flows between two bodies because of a difference in temperature. So temperature is kind of a sidebar to heat. So heat will always flow from a region of higher temperature to one of lower temperature. And then once the temperatures become equal, the heat flow will stop. And so what happens is heat will always flow to get temperature equality. So, if you've got your hot cup of coffee and the heat is coming out of it, it's warming up the air around it. Eventually, your cup of coffee goes cold, and it's going to be equal to the temperature around it. So again, let me point out that heat and temperature are oftentimes confused. People will talk about them as the same thing. But again, heat is the total energy of the molecular motion. So heat is the energy. The temperature is a measure of the average kinetic energy of the molecule. So temperature is really just a measure of heat. So they're not the same thing. So for example, if you have a gas and you heat it up, you add heat to it, you're transferring heat into the gas. What you're doing is you're speeding up the molecules. When you speed up the molecules, the average kinetic energy increases, and therefore the temperature increases. So the temperature is a measure of energy, and they are not the same thing. So let's talk about heat. Heat can either be given off or it can be absorbed. So when matter undergoes chemical reactions, you're going to, one or the other is going to happen. If heat is released, we call that process exothermic. Obvious reasons. Out thermic heat. So heat out. Q is often the symbol given for heat. I think we'll talk about that in just a minute, but heat will be negative. For example, when you have a combustion reaction, so they're showing you in this picture here, if you have an oxyacetylene torch, heat is being given off. That's an exothermic process. A change that absorbs heat is called an endothermic process. Heat is positive. Q is the symbol for heat again. Q is positive. For example, when you crack a cold pack, you're mixing chemicals that actually absorb heat from the surroundings to make that reaction occur, and so you're feeling it getting colder. So that's an endothermic process. So in a chemical reaction, heat is often transferred from what we call the system, which is generally the what we're talking about, the chemical reaction, to its surroundings, or vice versa. So if it's exothermic, the heat will be given from the system to the surroundings. And if we have an endothermic system, the heat will transfer from the surroundings to the system. So the system, again, is just the what we're studying. So it's the substances under study, the chemical reaction that's happening. And then, of course, everything else is the surroundings. Technically, you know, mainly when we're talking about the surroundings, we're talking about just right outside the reaction. But, of course, the surroundings could be everything. It could be the room. It could be, you know, the tea in China or whatever. Anyway, so that's pretty easy to understand. The system is what's happening, what we're studying, and the surroundings is everything else. Okay, so consider a system where a reaction takes place. If the temperature of the system falls, that means that heat is flowing from the surroundings into the system until the two are equal again. So that means that Q is positive because heat is being put into the system, and it's an endothermic reaction. So the flask will feel cooler, just like our cold pack. It'll feel cooler because it's taking the heat from its surroundings into the system and making everything feel cooler. If the temperature of the system rises, that means that heat is flowing from the system into the surroundings, eventually until the two are equal. That means Q, the symbol for heat, is negative. It's an exothermic reaction, and the flask will feel warmer to the touch because heat is being released. I think we're repeating this one more time. So an endothermic process is a chemical reaction in which heat is absorbed, Q is positive, and an exothermic process is a chemical reaction or physical change in which heat is evolved, which Q is negative. So it doesn't have to be a chemical reaction. It says physical change. So of course, like, you know, so let's think about that. If you melt ice, is that endothermic or exothermic? So think about it. The ice requires energy to melt it, so it absorbs heat, and so that's an endothermic process. Melting heat is endothermic.